Okay, we're going to now introduce a very important type of mathematical objects called matrices. And then we'll also perhaps go into the binomial coefficients. These are in lecture notes, matrices and binomial coefficients. So A is a matrix. With entries in a set R. What that means, A is a collection of Aij, where Aij is the entry in the ith row and the jth column. For integers I and j. And if I goes from 1 to m, and j goes from 1 to n. We say A is a m by n matrix. And we're merely going to concentrate on a square matrices. So we denote m sub n of R. It's a set of all A. A is a n by n matrix with entries from some set R. And usually R might be the integers, could be the rational numbers, the real numbers, or C. And we can add matrices. That's pretty easy. If A and B are matrices, where Aij and Bij are the elements, A plus B is very easy to define. That's just the matrix whose ij entry is you just add the ij entry of A plus the ij entry of B. And if, say, alpha is an element of R, we could multiply a matrix by an element by saying I alpha times A, you would just multiply every single entry in A by Aj. Again, this is some more details in the notes, including in 2x2 cases how we define it for 2x2 cases. We can also define the product of A times B, and that's a little bit trickier. So let's first look at an example. So in this example, take a 2 by 2 matrices, you add them 1, 2, 4, minus 1, plus 3, 2, 5, 4. It would just be 4, 4, 9, and 3. Pretty straightforward. Multiplication's a little bit trickier. So how do we multiply the matrix? What you do is you may have encountered the dot product. If you think of this as a vector 1, 2, and this as a vector 3, 5, and you took the dot product, it would be 1 times 3, 2 times 5. And that's the entry here, 1 times 3 plus 2 times 5. And then you get the first row against the second column, gives you the first row, second column here. So that would be 1 times 2 plus 2 times 4. So again, not as simple as just adding the matrix. You don't multiply each entry in A by each entry in B. And then 4 times 3 plus negative 1 times 5. So to get what's in the product, how do you find the second row, first column? It's the dot product of the second row of the matrix on the left by the first column of the matrix on the right. And then similarly here, second row, second column is a dot product of the second row of the matrix on the left and the second column of the matrix on the right. So 4 times 2 plus negative 1 times 4. And so this would be 3 and 10, so hopefully that's 13. And that would be 2 and 8, which is 10. And then that would be 12 minus 5 would give us 7. And 8 minus 4, which would give us 4. So that's how you would multiply matrices. Is this commutative? Does the order we multiply the matrix matter? Well, let's see in this case if it makes a difference. And so we're looking for a counterexample. Maybe this will not give us the same result, in which case that would be sufficient to show that the matrix multiplication is not commutative. But if it is, that doesn't mean necessarily matrix multiplication is commutative. We'd have to maybe investigate some further example, or maybe if we really think that, we should try to prove it. So let's go with this. This would now be 3 times 1 plus 2 times 4. And there'll be several other entries, but let's just, that's 3 plus 8 is 11. So automatically we see we get a different matrix. And maybe just for practice we can multiply this out. 3 times 2 plus 2 times negative 1. 5 times 1 plus 4 times 4. 5 times 2 plus 4 times negative 1. And so that should give us 6 minus 2 is a 4. 5 plus 16 would give us 21. And 10 minus 4 would give us 6. So again, that's a 2 by 2 case, which we really will spend a lot of time working in the 2 by 2 matrices. Let me just provide a general definition. So again, AB, as on that previous board, A equals Aij, and that's a matrix. B equals Bij, which is also an n by n square matrix. And their product, A times B, is a Cij. So how would we express this Cij? Cij, well, I is the row. The row all comes from the ith row of A. And the j, that comes from B. That's the jth column of B. So it would be AI 1 times B 1j plus AI 2 times B 2j, all the way up to AIN times BNJ, which I believe in the notes I gave that a summation notice. That's really, you can introduce another subscript, say k going from 1 to n of AIK BKJ. And in general, AB is not equal to B times A. So as objects, that's a way that the matrices differ significantly from numbers. So we also talk about a matrix, and there's something called the identity matrix. So we define the identity matrix in the n by n matrix to be what we have is we have ones down the diagonal and 0 everywhere else. And we denote the identity matrix by I sub n. So more mathematical definition, you could say I sub n is equal to well, maybe let's introduce the variable, say, xij for the ij entry of it. Where xij is equal to 1 if I is equal to j, and 0 if I is unequal to j. So that's just sort of a way of notating matrices down the diagonal. The 1, 1, the 2, 2, the 3, 3 entries would all be 0. 1 would all be 1s, and everything else, the 2, 1, 1, 2, etc., would all be 0. And this identity matrix, it's similar to the same role that 1 plays in multiplication. So note for any n by n matrix, AI is equal to A, or I sub n, and I sub n times A is also equal to A. So in some ways, the role that 1 plays in the multiplication of number, the n by n matrix plays in matrix multiplication of n by n square matrices. And we can maybe even try to prove this, or just sketch why would this be true. So if A is represented by Aij, then A times In has as the ith entry would be A1 or AI1 times X 1J plus I2 times X 2J, etc., up to AIN X NJ. But most of these AIJs are equal, right? Or 0. A1J is 0, except when J equals well, that's going on here. This is AKJ equals. So this would only be equal to 0 if J was equal to 1, and everything else would be. So this is all equal to 0 except when K equals J. So the only term that survives is when this index here is K, which would, when K equals J, so you'd have AIJ times 1, or AIJ. So what I've basically shown is that A times IN, the ith J entry, is just the same as the ith J entry of A. And point out this is like a bonus DVD material, so I don't think I've left this short calculation out of the notes. So just like numbers, if you have 5, you can multiply by 1/5, and that'll take you back to 1. What matrix can we multiply matrix A by to take us back to 1? And so what we do is we define the inverse of a matrix as the matrix A inverse with the property that A times A inverse takes you back to the identity, and A inverse times A also takes you back to the identity, if such a matrix exists. I also put out the following, that if n is negative, we can think of a to the n is just a inverse to the negative n, where negative n would be positive. So I mentioned this definition holds if such an element exists. Well, how can we tell? Okay, well, given a matrix, we can define the determinant of A, denoted by det of A, and it turns out that A inverse exists if and only if the determinant of A is not 0. And also if A, B are matrices then if we take the determinant of the product, that's the same as taking the determinant of A times the determinant of B. Let me actually add to this definition the determinant of A, denoted by this, which, or with, the determinant of this is not a matrix, it's a number. It comes from R. So I point out here, these are two different multiplications. AB is a multiplication of matrices, n by n matrices. Determinant of A times determinant B is multiplication down in whatever number system you're working in. Usually the reals or the complex numbers, rationals or integers. And we will not define the determinant of the n by n matrix, but if A is A, B, C, D, a 2 by 2 matrices, we will define the determinant of A is just AD minus BC. And then A inverse is just 1 over the determinant of A, that's a scale number, and then times the matrix AD, and then B and C pick up negative signs. So these two entries switch, these two pick up negative signs, and then you also have to multiply the entire matrix by the number 1 divided by 1 over the determinant. And so you notice that since the determinant is not 0, 1 divided by a non-zero number will still be a number. And again, in the notes I verified this calculation. So that's a little bit about matrices, and we will do some examples with these, particularly the 2 by 2 matrices. Okay, then the last type of thing of background I'd like to give is just the binomial coefficients. So we look at that. So to first set this up, we define what's called n factorial. So this is denoted by n with an exclamation point. And let me check the screen, make sure I'm still on there. So 0 factorial is by definition 1. And n factorial is n times n minus 1 factorial. For n greater than or equal to 1. So 1 factorial is just 1 times 0 factorial, which is 1. 2 factorial is 2 times 1 factorial, or just 2 times 1. 3 factorial is 3 times 2 factorial, or 3 times 2, which is 6. 4 factorial is 4 times 3 factorial, which is 4 times 3 times 2 times 1, etc. So you think of n factorial as just n times n minus 1, all the way down to 1. And again, you may have seen these in probabilities. They come up sometimes if you think of, suppose you have 4 different cards, how many different ways can you put them in various orders? Well, there's 4 choices for the first, what card can go on top. Each of those has 3 choices for the next card. Each of those has 2 choices for the third card. And then once 3 cards are placed, there's only 1 choice there. So this is 12 times 2 is 24. So basically there are 24 ways to write A, B, C, D, four different elements in the list. So that's the factorials, and we're going to use those to define what are known as the binomial coefficients. Again, also another place we've seen these factorials in the calculus curriculum. They are involved in tail of polynomials, right? They work out exactly what you need to sort of have the tail of polynomials match the nth derivative. The nth differentiated tail of polynomial n times to find that its derivative agrees at the center of the Taylor series with the function's nth derivative at that point. So now we define the binomial So that's defined by, so they put this bracket here, n over k, and that's n factorial over k factorial over n minus k factorial. And sometimes this is read as n choose k. So those are the binomial coefficients. Just n times 0, n choose 0, what would that be? N times 0 factorial over n minus 0 factorial. So n factorial over 0 factorial over n factorial. These cancel, so it's just 1 over 0 factorial or 1. So n choose 0 is 1. N choose 1 would be n factorial over 1 factorial over n minus 1 factorial. But n factorial is just n times n minus 1 factorial. 1 factorial is 1. So these cancel, and we have n. Let's also look at maybe another calculation. N choose n minus 1. So that's n factorial over n minus 1 factorial times n minus 1 factorial. So that's n factorial over n minus 1 factorial over this n cancels, it would just be 1 factorial. And that looks basically the same as that, except for the order we've multiplied the two numbers in the denominator. So we have this. Again, if you think about choosing n minus 1 elements from an n element set is really the same as choosing one element from the n element set, namely, choose which element you leave out. The number of ways you can leave out one element is going to be the same as the number of ways you can pick all but one element. So this generalizes to Pascal's identity. If we have two integers, n and k, with k greater than or equal, n greater than or equal to k, and both greater than 0, n choose k is the same as n choose n minus k. So that's Pascal's identity. Sometimes called Pascal's formula. Again, so the binomial coefficients you can think about are the number of ways to select k elements from an n element set. And you can see maybe why, if you have an n element set, picking 3 elements is the same as picking n minus 3 elements. Because number of ways you can pick all but 3 elements are the same exact number as the number of ways you can pick all but 3 elements. So let's begin by proving this. So the proof of Pascal's identity. So we look at, I'm sorry, that's not Pascal's identity. That's let's just not give it a name. So let's just call it proof of So this would be n choose k is just n factorial over k factorial times n minus k factorial. But this is really the same as n minus k factorial. We write that here. And then we can rewrite k factorial as n minus k factorial. But this is exactly n choose n minus k. So I shouldn't have called that Pascal's identity. That's just a binomial identity. I'm not even sure if it has a name. Pascal's identity usually refers to this. Again, the same setup for n and k integers with n greater than or equal to k and k greater than or equal to 0. n choose k plus n choose k minus 1 is equal to n plus 1 choose k. So that's Pascal's identity. And before I prove this with a computational, it's pretty simple, but what's the idea behind this proof? Why would this make sense? So you have n plus 1 elements. And you want to take a k element subset of that. Well, let's take one element and say, okay, let's label the elements. Suppose the elements are labeled 1 through n. Let's take 1. Okay, we're going to put 1 in the subset. How many different subsets can there be from 1? That contain k elements. Well, we have 1 in there, so we can pick k minus 1 from the n. The number of ways we can pick this, you can think of this as being the number of k element subsets that automatically will have 1 as an element. Then we can, so that's some of the n plus 1 element sets, all the ones that have 1 as an element. Then let's look at the ones that don't have 1 as an element. So we're going to leave 1 out. So we still have k slots to fill, but now we can only pick from n elements because we have to exclude 1 so we can pick from the rest. And there's no overlap between these two sets, right? These sets all don't have 1 in them. These sets all do. So the number of ways we can write k element sets that contain 1, plus the number of ways we can take k element sets that don't contain 1 and we add them up, that's going to be the number of ways we can take a k element subset out of these n plus 1 elements. So let's prove this. And again, it's just computationally. This is in the notes. Okay, we'll put in quite as much detail. So this is n factorial over k times n minus k factorial plus n factorial over k minus 1 factorial times n minus a k minus 1, so minus k becomes a plus 1. We subtract this, negative k plus 1. And we want to add these, so we need to get a common denominator. So what do we have here? We've got all the factors up to k. Here we're missing a k, so we need to multiply this by k. And I do the same over here then. Keep that up, multiply that by k. Then what about this set here? Well, here I've got everything up to n minus k plus 1. Here I stop 1 short. I have all the factors up to except that 1, so I'd have to multiply the denominator by n minus k plus 1. And to keep the value of the fraction the same, I multiply the numerator by that. And again, the notes provide this in some more detail, a little bit more step by step. So now we're going to have a common denominator. What's our common denominator? These two are the same. And those two are the same. So basically we have, oh, I've forgotten the factorial sign here. We basically have k factorial over n minus k plus 1 factorial. And in the numerator, we'd have n factorial, n minus k plus 1, and then a plus n factorial times k. So this becomes n factorial if we just combine terms. N minus k plus 1 plus k, that's just going to be n plus 1. And the denominator stays the same. But this is n plus 1 factorial over k factorial, and I'll just rewrite this as n plus 1 minus k factorial, right? N plus k plus 1 is n, what did I, that would be a minus k here, and so that would be a minus k there. And this is exactly n plus 1 choose k. So again, that's a proof of it. And so using Pascal's identity, one can prove the binomial formula. These lines are just there. Match up. So what is the binomial theorem? Given two real numbers, a plus b to the n is equal to a to the n plus n choose 1, a to the n, b to the 1, plus n choose 2, a to the, this is a to the n minus 1, that would be a to the n minus 2, chose 2, all the way up to n times n minus 1, a to the 1, b to the n minus 1, and then finally 1, b to the n. Or, when I use summation notation, a, b to the n is the summation k going from 0 to n of n choose k, a to the n, or a to the k, b to the n minus k. Which is also equivalent k to the 0, k going from 0 to n of n choose k, a to the n minus k, b to the k. Often this is sometimes usually the way it is written. The reason for that, it looks like I switched these two, but I didn't switch this. But remember, we have the this binomial identity that really I did switch. You know, n choose k is the same as n choose n minus k. So we'll prove this by induction. And maybe again, I'll give you a little more bonus material. Let's first see how we can get some of these numbers. So first, in terms of getting the numbers, device called Pascal's Triangle. You put a 1 here, and then a 1, 1. I think of this AB to the 0 is just 1. AB to the 1 is 1A plus 1B. Then you put another 1 here, another 1 here, and these two we add together to get 2. AB squared is A squared, 1A squared plus 2AB plus 3 plus 1B squared. Then another one here, these two get to 3. 2 and 1 is also 3 and then 1. So AB to the 4th would, AB cubed, AB to the 3rd would be 1A cubed plus 3A squared B plus 3AB squared plus 1B cubed. And again, 1 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4, another 1 down the diagonal. So AB to the 4th would be 1A to the 4th plus 4A cubed B plus 6 A cubed B cubed plus 4A squared B, and finally plus 4, wait, my mistake here. This is right, this would be 2 and 2, and then that would be 1 and 3, and finally just 1 B cubed. And this is called Pascal's Triangle. So it's related to the binomial coefficients. The way you can actually get those coefficients are from Pascal's Triangle. So let's prove of the binomial theorem, or the binomial formula. So again, Pn will just be the statement AB to the n equals, and I'll use the notation I did in the note, n going from 0 to n. We'll do n choose k, but we'll start out with a to the n minus k. E to the k. So the basis, we can either start at 0 or start at n equals 1. A b to the 1 is just ab, which is n choose 1, a to the, well, 1 choose 1, a to the 1 minus 0, or 1 choose 0, a to the 1 minus 0, b to the 0, plus 1 choose 1, a to the 1 minus 1, b to the 1, and 1 choose 0, 1 choose 1 is 0 or 1 respectively, so that's just a plus b. So I guess in my proof technique, I should probably stop here and put an n. Because these two are not equal to actually go through the calculation. So we see, so P1 is true. Okay, now let's begin the inductive step. So we assume Pn is true. Try to prove Pn plus 1. Let me make a correction again to these notes, or more in addition. When I applied the binomial theorem, in the statement of it, I should have added for all positive integers, and I guess it's actually true for n equals 0 as well. In fact, the binomial theorem is actually true for other values, non-integer values, but we won't cover that, and they're not included by the proof. So anyway, that's a change in the binomial theorem in that I never specified what n was. N has to be an integer greater than or equal to, well, you could take 1 or you could take 0. Okay, so let's look at the proof of this now, of the inductive step. So again, I apologize for the initial writing of the binomial theorem. I never specified that how at n was an integer greater than or equal to 1, or greater than or equal to 0. So let's see how we can approach this. So a plus b to the n plus 1 is ab to the n times a plus b. And so what we have this by the binomial, by the assumption of the binomial theorem, this is n choose k, a to the n minus k, b to the k, where k goes from 0 to n. And that's equal to a times b. Oh, that's multiplied by a times b. But what's going to happen here? Well, we think about the first term when you have a n to the 0, that's a 1 a n times a, so we're going to have an a to the n plus 1. And then we're going to be left with k going from 1. And let's not stop at n, let's stop one short, n minus 1. And that would be n choose k. And this is a n minus k plus 1 for the other factor of a, b to the k. So that's one term in the sum. And then going to have that, and that's still going all the way, and we can actually take that all the way up to the nth term of it. So we'll go all the way to the end, and that takes that part. And then we have another sum. We'll start at k equals 0. And now we've got all these terms from n to n minus 1. We'll leave out the last term. And it would be n choose k of a to the n minus k times b to the k plus 1. And finally, the last term is just n choose n, which is 1, b to the n. And multiplied by this b would be b to the n plus 1. So we have that. And now what I'd like to do is I'd like to change the index. If you think about this sum here, I'd like to get them to agree. And here maybe I will say that's a to the n plus 1 minus k, b to the k, so I'll leave that one alone. And now what's the first power of a? Well, it starts off at n minus 0, or just 0, or just n. And then the coefficient would be n choose 0. So if I want to start my sum at k equals 1, I would go to n. But now this should be k minus 1. And this would also be n. Initially, I start off subtracting 0. So if I'm going to put index of 1 here, if I'm going to start my index off at 1, I want to subtract k minus 1. Basically, I've replaced k by k minus 1. And finally, it ends. Where should it end? It should end when this subscript is n minus 1. So that would end when k equals n. And then my b subscript, k plus 1, this starts out at 1 when k equals 1. And it ends at n, so now my b would just be k. And finally, I have outside the sum this last term. So really what I've done in that sum, I've just replaced k by k minus 1. K going from 0 to n minus 1 is the same thing as k minus 1 going from 1 to n. So I replaced this k by k minus 1, and I did this k as well. Maybe I should put in replace k by k minus 1, but then there's a plus 1. So then when the dust settles, what am I left with? Also, here I miscopied, this is an plus 1. So it would be an plus 1 plus summation k going from 1 to n of n choose k plus n choose k minus 1 a to the n plus 1 minus k, that is some distributing, and after simplifying that, that's just b to the k plus b to the n plus 1. But by Pascal's identity, those binomial coefficients combine to n plus 1 choose k. So what have we done? We started with AB to the n plus 1, and we've shown it is equal to this. This is Pn plus 1. So by the principle of mathematical induction, right, we've done a basis case. We could have started at 0, we started at 1, and then we've assumed that Pn is true, and we've derived Pn plus 1 is true, so we've done the inductive case. So by the principle of mathematical induction, the binomial theorem holds. And AB to the n is the summation n going from 0, k going from 0 to n of n choose k, a to the n minus k times b to the k. For all integers n greater than or equal to 1, though it also holds for n equals 0. So I'd like to include for one last thing that's needed in a homework problem, and that's the definition of a binomial coefficient in a case where you have what would -3 choose to be. So let's generalize the definition of binomial coefficients. These generalize to all sorts of numbers, but let's restrict. We expand our definition of n choose k to the case where n is a negative number and k greater than or equal to 0 by defining or setting, and this negative number n choose k is equal to -1 to the k, negative n plus k minus 1 all over k. Note, since negative n is less than 0, strictly less than 0, negative n will be strictly greater than 0, so it'll be at least 1. So negative n minus 1 is going to be at least 0. K is at least 0. So this binomial coefficient is defined. Negative n plus k minus 1 has got to be at least 0. And then what we do is we put a -1 to the k out in front. So that concludes the introductory material. We'll begin actually introducing the concept of a group. We'll have some lecture notes, should be posted shortly. And we'll conclude this lecture here.